For this section, we look at conditional probability, which is kind of confusing to some people, or if not confusing, sometimes the formula is hard to use. So as you'll see when we go forward, you really want to memorize the formula. And there's two varieties of it, very similar, but it's not hard to do, just a little practice. And then you want to do this in what's called a cookbook style, a plug and chug style, and I'll explain what I mean as I go along. So our formula that we're given here is the P, A, and then there's a straight bar B that's read as, what's the probability of A given B? And given B means B has already happened. So that is equal to the probability of A and B, that's the intersection of A and B, both have happened, divided by the probability of B. This is a formula you want to memorize, be able to write whenever you need to. The next thing you'll do is say, well, what's A and B? And once we identify that, we plug it into the formula and we can do the problem. Here it is, the pictorial form. A and B is the intersection between A and B, and that's that green shaded section. Probability of B is just the blue oval on the bottom. You don't even need the empty A circle. So now we have our contingency table, and it's been turned into a bunch of relative frequencies, which in our case are probabilities, and we're going to use this table. We're going to come back to it. So what was the probability of being audited given the income was at least $1 million? As soon as you say given, that's that, given B, at least $1 million, you know what B is. It's the income more than $1 million. The other part being audited being yes is event A. So let's see where these numbers come from. Let's look at probability A and B, 0.00027. Slide back. We say OK. Where's the probability? Right here. That's the intersection of being audited and more than $1 million. So it's literally what it says. These two intersect the row and the column. So we come back and we look again. We go, all right, what's the probability of B? Come back to it. And B is more than $1 million. You don't see that number. Look at the number again, 0.00249. But you can get the number pretty easily. It's the probability of B, which is at making more than $1 million. So if we look at this, more than $1 million, well, there's 0.00027 and 0.00222. That's where they've split that up into being audited and not. But if you add them together, you get the number here on the bottom. So plug it in. Top and bottom, use a calculator, do the division. That's about 11%. Now here we have a study of over 5,000 women over 35 analyzed using this triple blood test to see how accurate the test is. Women of this age are more at risk for having a child with Down syndrome. So let's make sure we understand it. The blood test can be positive or negative, but you can have mistakes. The D with Down in parentheses means they actually, when given birth, the child did have Down syndrome. And D with a C for the superscript is the complement, meaning they didn't have Down syndrome, unaffected. And you can see most of the time, even if they had a positive blood test, the child born did not have Down syndrome. But you notice when it was negative, it was far less kids who had Down syndrome. So the test is maybe useful, but it's certainly not far from perfect. So you should stop and read these and understand what's going on. We have false positives and false negatives. And here we're going to look at the total positives, which is 1,355 compared to the total women in the study, which was 5,282, and we're going to calculate that percentage, that probability of being positive, slightly over 25%, about 26%. Now we're going to do the same thing. We're going to look to see about the intersection between children who had Down syndrome, as predicted, and who had a positive test. And I've circled that for you, 48, compared to the total of 5,282. We have 0.009. Now, we have this probability of Down syndrome given a positive test. That's what the D bar, I guess you could call it. It's a Python symbol is what they're called, POS. Now if you wrote the formula, probability of A given B equal probability of A intersect B over the probability of B, you'd be set. All you'd have to do is plug in the numbers as we did before. When you actually do this calculation, it's about 3.5% of the women who tested positive who actually had children with Down syndrome. The multiplication rule that we've been using assumed things that were independent. So what's the probability of flipping a quarter 3 times and getting heads every time? It's 1/2 times 1/2 times 1/2. Happen 1 in 8 times roughly if you do it for a long time. Remember, short-term runs are not of interest to us for this type of probability. So we say the probability that A and B both occur. That's A intersect B or A and B. A more general expression is the one given here in the middle of the screen. The one on the top assumes that the events are independent, but in fact events are not independent all the time. So from the prior slide at the top we have the probability of A intersect B is equal to the probability of B times the probability of A given B. Now we can rearrange this conditional probability formula we started with by multiplying each side by the probability of B. That'll give us over here the probability of B. Here it'll cancel. We'll have probability of A and B, or A intersect B on this side. And over on this side we'll have probability of B times the probability of A given B. And I see here I've got a mistake, so I will fix that. So I'm going to pause it now and fix it. Okay, things are all fixed here. And you see the A and the B have reversed positions, so we can actually use either formula if we need to. And here's an example. This is on page 225, 226 in your book. And this author is going to use F1 and F2 for the 2 events, which makes sense for fault 1 and fault 2. But I'm going to show you after he goes through this how you could actually do it yourself and probably be a little less confused. So it gives the probability of F1, and that's 0.38. It gives the probability of a second fault, given that he does the first fault. That's much smaller. He's more careful on the second serve. And he works it all out. So now we're going to rework it. But we're going to actually say these are events A and B because that actually fits in our formula pretty easily. So using one of our formulas down here at the bottom, we say probability of A and B equals probability of A times probability of B given A. And we simply plug in the numbers we're given and we get our answer. And I think you'll find that's much easier to do it instead of every time trying to make up different terms. So sampling and outward replacement we went over earlier. And I think you're pretty clear on that, so I'm not going to spend any time on it. Independent events, well, they do happen, but not always. So if they're independent, we use this formula at the bottom. If they're not independent, we use the formula for conditional probability. So how do you know if 2 things are independent? Well, you look at this, you say, if the probability A given B equals the probability of A. In other words, if B's happened, was there any influence on A? How about if A's happened, was there any influence on B? Did it change its probability? If the answers are both no, you're in pretty good shape. Another way is, if you found the probability of A and you found the probability of B, and it was turned out to be the same as the probability of A intersect B, then they are independent. Goes back to his example here. I'm going to let you work on this one by yourself. Again, you should go to the book. Just see when he starts putting things in here. What's the probability of a positive test given Down syndrome? That actually helps with the understanding. But you may want to go back to the formula first just to be clear on which one's which. And that ends this section.